Alright, now we are looking at question 11 of the 2023 paper 1. Okay, so we'll continue from question 10. Okay, so for question 11, the rate of an enzyme catalyzed reaction changes as substrate concentration changes. Which row correctly describes how the rate changes and gives the correct reason why it changes in this way? Okay, so if you recall the enzyme catalyzed kinetics, right, the graph will look something like that. So we have rates over here, and then we have the concentration of the substrate. So it goes something like it increases and then it plateaus. Okay, it increases and then it plateaus. Okay, so if we look at all the option, we are probably looking at option C or option D. Increases and reaches a maximum value. Okay, and then we look at the reason. Option C reads activation energy is lowered. So again, yes, it's alternative pathway with a lower activation energy. And then over here they say something like, but cannot go below a particular minimum value, so don't really know what it's talking about. Okay, now what we understand is that the enzyme active sites, okay, if you just look at a simple model, right, it has various pockets, something like this, for your substrates to adsorb onto. Okay, so when you have 1, 2, 3 being occupied, any increase in substrate concentration, you will continue to increase the rate of reaction. But once your enzyme active site is saturated, if you further increase the concentration of the substrate, the remaining substrate will just have to wait until the catalysis is completed before the product dissolve from the active site, and then the substrate will then absorb onto the active site. So that is when you have the maximum rates of reaction. So the maximum rate occurs when the enzyme active site is saturated. Yeah, so I think option D will explain that the best, because all enzyme active sites are occupied at high substrate concentration. I think that summing up in a simplistic manner, but I think it works for an MCQ question. Okay, then we'll move on to question 12. The statement refers to the value of equilibrium constant Kp for a gas phase reaction. Which statement is correct? Okay, so again, we're going to look through all the statements. So statement A, adding a catalyst increase the value of Kp. Okay, so this is not correct. It allows equilibrium to be established at a faster rate, but it doesn't increase the value. Yeah, only temperature will cause the value of equilibrium constant to change. Okay, no other factors will. Right? Okay, B, changing pressure will decrease the value of Kp. Okay, so again, this is not correct. So equilibrium constant is a temperature dependent variable. Okay, doubling the pressure doubles the value. Okay, again, incorrect. Okay, so doesn't change. So I'm just looking out for an option that says that if I want to change the value of K, I must change temperature. Okay, so D, increasing the temperature decrease the value of Kp. Yes, that is correct, right? Yeah, because remember, for let's say from A to B, right? If it's an exothermic reaction, heat is released. Okay, so if I increase the temperature, yeah, the position of equilibrium. Okay, so before I talk further, let me just correct this. Okay, the position of equilibrium will shift in a direction so as to partially remove the heat being introduced. Yeah, so in this case, it will have to shift to the left. Yeah, so when you shift to the left, the value of Kp actually decreases, right? Because equilibrium constant is a ratio of product reactant. Okay, yeah, so it decreases the value. So I'm going to choose option D. Okay, question 13 is an equilibrium question. So we have gaseous reaction between nitrogen and hydrogen is carried out. At equilibrium, the temperature is 400 Kelvin. Okay, equilibrium total pressure is given to be 100. So let's take note at this. Initial mole ratio of nitrogen to hydrogen is given to be 1:3. This is important as well. Do note that this is mole ratio, not number of moles, so we have to take note of it. Okay, and of course the partial pressure of ammonia at equilibrium is given to be 92. If they do not give you this, then you realize that you'll be running into a little bit of issue in solving. Okay, they gave you the reaction between nitrogen and hydrogen to give you ammonia. That's a Haber process. Question asks you what is the equilibrium constant under these conditions. Okay, so the student did it assuming that the number of moles is 1 and number of moles of hydrogen is 3. That is actually okay as well, but maybe a slightly more proper way of doing this question is to let the unknown be A:3A. Yeah, but I prefer to work in terms of partial pressure. Yeah, that will be easier. So I'm just going to illustrate in the space below. Okay, so that you'll be clearer for everyone watching the videos. Okay, so we have nitrogen, hydrogen, and ammonia. Okay, so we have initial partial pressure. So I'm just going to indicate it with atmosphere. Okay, so initial P in terms of atmosphere, change in P in terms of atmosphere, and equilibrium partial pressure in terms of atmosphere. So I'll let my unknown be A, so that this will be 3 A:3A, so this will be 0. I'll let my change be x, so that's minus x minus 3x and 0 as well. Oh sorry, not 0, plus 2x. Okay, and then equilibrium partial pressure, that will be A minus x, 3A minus 3x and 2x. Okay, I was told that the equilibrium total pressure is 100 atmosphere, so I'm going to draft out an equation. So that will be, I will sum up all of these. Okay, so that will be 4A minus 2x equals to 100. Right, I am also told that the equilibrium partial pressure of ammonia is 92. So in this case, 2x is equals to 92. Okay, so x will be 46, but we might not need to work that out. Okay, so that means that 4a is equals to 192, so a is equals to 48 atmosphere. Okay, so with this particular details, with the Kp expression, so Kp will be equals to the partial pressure of ammonia squared divided by the partial pressure of N2 multiplied by the partial pressure of H2 cube. Yeah, I can then continue with my calculation. So that would be 92 squared divided by partial pressure of nitrogen, 48 minus x, which is 46, so that will be 2 multiplied by a minus x is 2, so 3 times 2 is 6, so that will be 6 cubed. Okay, so I'm going to punch my calculator, and of course the value I'm going to get will be 19.6 atm minus 2. Okay, so that will be this answer. Okay, so in a structured and free response question, we really have to be a little bit careful in the presentation of our answers. Yeah, but for MCQ, then we can probably we can do it the fast way by what was presented by the students. But ideally, it shouldn't be a 1 to 3, because that will be an assumption. Okay, yep. Okay, question 14. Okay, the use of data booklets is relevant to this particular question. Yeah, this is actually a redox question. Most of the time, the students tends to be not so strong in this kind of question. Yeah, I mean, there are a lot of reasons. You guys learn this at the start of JC1. I mean, some of the schools actually learn it at the beginning, some of the schools learn it after the foundation topic. Yeah, sometimes it's difficult to get the logic. Okay, so it does take a bit of time to get used to the way things work. Yeah, so probably I think you might, if you get this wrong, you might just want to go through a little bit more practices lah. Yeah, so but anyway, we'll just look at what the question entails, and we'll try to solve it accordingly. Okay, right. Okay, so we are given that we have 30 cubic centimeters of 0.5 moles per linear cube of bromine. Okay, yeah, so if you do a simple calculations in terms of number of moles, so that will be 0.03 times 0.5, then you should get a 0.015 moles of Br2. Okay, so I'm just going to write it out over here. 0.015 moles of bromine. Okay, it reacts completely with potassium hydroxide. So this is a basic medium to form 2.98 grams of KBr. Okay, so the other product is BrOX and H2O. Okay, so based on 2.98 grams of KBr. Okay, so we'll need the data booklets. Okay, so let's find the relative formula mass of KBr. So potassium is 39.1, bromine is 79.9, so that will give me 119. Okay, so 2.98 divide 119, yeah, we get 0.0250. Okay, so that will be 0.0250 moles of bromides. Okay, yeah, and question asks you what is the value of X in the formula. So in this case, the charge should be BrOX minus. Okay, then I'm going to write out the unbalanced equation. So that will be Br2, and then I'm going to leave a bit of space. If I want to write the overall balance equation, I can, but I do not really need to do it over here. Then my product is Br minus plus BrOX minus plus H2O. Again, if I want to write in the H2O, I can, but it may not be the most important thing right here. Okay, so what is important is this particular ratio, 0.015 is to 0.025. If we do a quick comparison, that will be a 3 to 5 ratio. So this is going to be 3 is to 5. So with that, we can straight away write in here 3 is to 5. Okay, you notice that in terms of material balanced, okay, simply by material balance, in terms of bromine, it is already balanced, the 3 to 5 ratio. Alright, so since it's already balanced, let us take a look at the change in oxidation state. Okay, so you notice that bromine goes from 0 to -1 over here. Okay, so that means that the bromine gains 1 electron. Yeah, so you just think of it this way. 5 of the bromine, I know it's in terms of Br2, but I'm just going to use a very simplistic layman term. So assuming that we have 6 bromine, okay, each of the bromine's oxidation state at the beginning is 0. 5 of it becomes -1, so 5 of them gains 1 electron. Okay, but these 5 bromine, right, okay, gain electrons from where? Okay, from the remaining bromine, right? Correct, because these 5, each of them will gain 1 electron, so this bromine will donate 1 to each of the 5, so this is become minus, and then it, to some extent, this become like a +5. So that means that the bromine here must have an oxidation state of +5. So for it to have an oxidation state of +5, X must be 3. Am I right to say that? Okay, you can do a quick calculation if you want. So BrO3 minus oxidation state of bromine is +5. Okay, so with that alone, I have already balanced this equation and successfully determined what X is, which is +3. Okay, if you want to do the full balancing, you can. I'm going to write in green. Okay, yep, it is as it is. So there are a total of 6 minus 6 on the right hand side, so I'm going to add 6 OH minus. Okay, yep, and as per all cases, the water will balance on its own, so there will be 3 H2O over here. Okay, so you can do a checkout to see whether everything is intact. If there's any issues, you can raise in the comments below. Okay, next question 15. 2 students are each given equal volumes of 0.1 moles per day of silver nitrate, sodium ethanoate, and potassium bromide. Okay, so seems to be like a KSP kind of question, so we're going to continue to read it. The first student mixes sodium ethanoate and silver nitrate, obtains a white PPT. Okay, so what am I expecting? Probably silver ethanoate. Okay, on adding potassium bromide to this mixture, the white PPT dissolves and cream PPT is formed. So that means that, can I say that silver bromide is more insoluble as compared to silver ethanoate? Can I say that? Yeah, so you can draw this conclusion from here. Okay, so in terms, so I can say silver bromide more insoluble than silver ethanoate. Okay, I'm going to write it here, CH3 CO2 minus Ag plus. Okay, the second student adds silver nitrate to potassium bromide, so I'm going to get silver bromide. And then when I add sodium ethanoate, no further change. Yeah, so this okay, so 1 and 2, right? So 2 also prove this. So which statement explains? Okay, so I think first of all, silver ethanoate is insoluble. This is definitely correct. If not, you wouldn't get the white PPT. Silver bromide is less soluble than silver ethanoate. Okay, so this is correct also. Proven by point 1 and 2. Ethanoate can oxidize bromide. This is nonsense, right? Because I don't get any bromine. Did I get any bromine? I don't get bromine, right? So 3 is definitely wrong. So the answer is 1 and 2. Okay, gonna move on. Question 16. We have propane, benzene, ethane, contains carbon atoms with hybrid orbitals. So if we want to, we can write out the formula here. So C3H8, then we have benzene, and then we have ethane. Okay, so this one should be sp3, sp2, sp. The question asks, what is the total number of 2p orbitals hybridized with 2s in one molecule each? Okay, so sp3, so that will be 2p, okay, for each carbon. So 3 2p for each carbon, so total will be 9. Yeah, then for the benzene ring, there are 6 carbons. Each carbon is sp2, so there will be a total of 12 2p's. And then for ethane, okay, ethane is actually sp hybridized, 2 carbon. So each carbon will require 1 2p to hybridize with it, so that's 2. So if you sum them up, that will be a total of 23. So the answer is C. Okay. Question 17. You have chloroethene is unreactive towards nucleophile. Okay, of course it will be repelled away by the CC pi bond. And then 3-chloropropene, okay, is very reactive. Okay, so over here this carbon is delta plus. Okay, then of course you have delta minus over here. Yeah, which statement best explains the lack of reactivity? Again, best explain. So we have to choose the best option. If it's a structured free response question, I think it's worth about 2 to 3 marks. Yeah, but in this case, we are just going to choose the best answer. Okay, and we strike out the obviously wrong answers. Okay, so we look at A. All substituted alkenes undergo only electrophilic addition. So again, this is not very generic. It's not explaining anything, so we're going to cross this out. Okay. The CC double bond and the Cl are both electron withdrawing. Stabilize this. So again, I think it is almost unheard of saying that the double bond is withdrawing. Cl is indeed withdrawing. Stabilize this. How does stabilizing this helps in its lack of reactivity to nucleophiles? It's not really explaining much as well, right? Yeah, so again, B is out. C electrons in the p orbital of the chlorine overlaps with pi bond. Okay, so I think in a more accurate language, the lone pairs delocalize across the CC pi system, strengthening the CCl bond. So the strengthening part actually helps to explain the lack of reactivity. So I think this will make a bit of sense. Okay, not complete, it's part of it, but it makes a bit of sense, right? Presence of the pi bond prevents free rotation. So again, the free rotation here is not going to affect its lack of reactivity. Yeah, because it is the carbon in question that is susceptible to nucleophilic attack. It's not about the bond. Okay, so again, this is nonsense. Yeah, so the answer will be C. Okay, question 18. How many constitutional isomers are there with the formula C5H10 that do not contain carbon atoms in a ring structure? So they limit your answer. So I can only have double bond. So again, you do a quick calculation. You have 1 degree of unsaturation. So it's calculated by the students. Okay, what is the best strategy to do it? Again, you draw a straight chain. You draw a branch. Okay, and then you see where you can place your double bonds. Okay, I cannot branch further because if I branch further, okay, I'm just going to show you, then I can't put my double bond anywhere. Okay, so branching further will not help, so I'm just going to remove this. Okay, so my double bond can be here. Okay, so that's one position. Okay, my double bond can potentially be here. Okay, as well. My double bond can also potentially to be here. Okay, but purple and yellow, are they the same thing? I think they are the same thing, right? So I'm just going to remove the yellow ones. Okay, so 2 position for the straight chain. Okay, then for the branch, potentially I can 1 here, 1 here, okay, and another 1 here. So that's 3. Okay, so altogether we have 2 plus 3, so answer is 5. Okay, yep. Question 19, the use of the data booklet is relevant. Okay, I think it's about substituent effects. 2 reaction sequences with benzene as a starting material are shown. Okay, so one going to the left, the other one going to the right. Okay, what could be intermediate X and Y? Okay, so I mean, I like to look to the right, so I'm going to do this first. Okay, so this is electrophilic substitution. I'm getting the CH3 group in. The CH3 group, okay, is going to direct the incoming electrophile to the 2nd or 4th position. But over here, it is obvious that the relationship between CH3 and carboxylic acid is 1,3. Yeah, so in order for that to happen, I must ensure that my Y, okay, contains an electron withdrawing group, okay, that will be able to direct the next incoming electrophile to the 3rd position. Yeah, so my Y must be benzoic acid. Okay, so that means I must cause side chain oxidation to occur. Okay, and then I perform electrophilic substitution using chloromethane. But in this case, because benzoic acid is less reactive as compared to benzene, the condition to be used must be harsher. Okay, so that will leave me with either option A or C. Yeah, I'm not going to play poker by directing the incoming electrophile to the 3rd position using methyl, because that is highly unlikely that number 1 is that I'll be able to get substantial amount of product. And then number 2, it's difficult to control side chain oxidation from Y to the 1,3 product. Okay, so therefore the best bet is to ensure that Y is benzoic acid. Okay, next. Okay, I'm going to do something here so that I'm going to create an NO2 or a Cl, so it depends. So again, you have to ask yourself one question. If I add Cl, the Cl will direct NO2 to the second position. If I add NO2 first, the NO2 will direct the Cl to the third position. So therefore, my X must be chlorobenzene. Yeah, so I base my reasoning simply by looking at which one give me a higher proportion of the products. Okay, so therefore I'm going to choose X to be chlorobenzene. I'm not going to choose this. Okay, so I will choose option A as the answer. Okay, right. Question 20. Which statement about benzene and its properties is correct? Okay, benzene undergoes nucleophilic substitution. This is nonsense. Should be electrophilic substitution. Benzene molecule is planar, so hydrogen can easily undergo addition reaction with it without the use of catalyst. Again, nonsense. It doesn't happen. Benzene does not want to undergo addition so readily. Okay, the pi electron in benzene are able to donate an electron pair to attack a carbocation to form a bond. This is true, right? Yeah, so for example, in Friedel-Crafts alkylation, if I have an electrophile, for example, CH3+, yeah, then the electron-rich benzene ring will then donate its electron pair towards the carbon. Am I right to say that that is what you have learned from the lecture? Okay, yeah. Then donkey, the sideway overlap of p orbitals in benzene means the CC alternate between long and short. This is nonsense also, not correct. Yeah, all the CC bond in benzene are of the same length and strength. Yeah, so remember, we say that benzene is resonance stabilized. That explains why. Okay, so that will be the end of the debrief to part 2. We're going to continue with from 21 to 30 next.